Welcome to RF Basics Part 2, where we'll explore the essential components and circuits that make RF systems work. In this lesson, we'll cover the fundamental building blocks of RF circuits, including resistors, capacitors, inductors, and how they behave differently at radio frequencies compared to DC and low-frequency applications. Before we dive into specific components, let's understand why RF components behave differently from their low-frequency counterparts. At radio frequencies, which typically range from 3 kHz to 300 GHz, several phenomena become significant that we can usually ignore at lower frequencies. First, parasitic effects become significant. Every component has unwanted characteristics. Resistors have inductance and capacitance, capacitors have resistance and inductance, and inductors have resistance and capacitance. At low frequencies, these parasitic effects are negligible, but at RF frequencies, they can dominate the component's behavior. Second, the skin effect becomes important. At high frequencies, current tends to flow only on the surface of conductors, effectively reducing the cross-sectional area available for current flow. This increases resistance and affects the behavior of inductors and transformers. Third, transmission line effects appear. When the physical dimensions of circuits become comparable to the wavelength of the RF signal, we can no longer treat connections as simple wires. They become transmission lines with characteristic impedance, propagation delay, and reflection effects. Let's start with RF resistors. While resistors might seem like the simplest components, they present unique challenges at radio frequencies. An ideal resistor would have a constant resistance value regardless of frequency. However, real resistors at RF frequencies exhibit parasitic inductance and capacitance. The leads and internal construction create small amounts of inductance, while the resistive element and its packaging create parasitic capacitance. These parasitic effects create a more complex equivalent circuit. Instead of just a pure resistance R, we have a series inductance L in series with the resistance, and a parallel capacitance C across the entire component. At low frequencies, these parasitics don't matter, but as frequency increases, they begin to dominate. This equivalent circuit shows how a real resistor behaves at RF frequencies. The series inductance causes the impedance to increase with frequency, while the parallel capacitance provides a path for high-frequency currents to bypass the resistor entirely. Every resistor has a self-resonant frequency where the inductive and capacitive reactances cancel out. Below this frequency, the component looks mostly resistive. Above this frequency, the component may look more like an inductor or capacitor, depending on which parasitic dominates. To minimize these effects, RF resistors are designed differently from regular resistors. Carbon composition resistors have relatively low parasitic inductance but can be noisy. Metal film resistors offer better noise performance and stability. For the highest frequencies, chip resistors in surface mount packages minimize lead inductance. Now let's examine RF capacitors. Capacitors are fundamental to RF circuits used for coupling, decoupling, filtering, and tuning applications. An ideal capacitor would have impedance that decreases linearly with frequency according to the formula 1 over j omega c. However, real capacitors have parasitic series resistance and inductance that limit their high-frequency performance. The equivalent series resistance, or ESR, represents the resistive losses in the capacitor. This includes resistance in the leads, plates, and dielectric material. ESR causes power dissipation and limits the Q factor of the capacitor, which is important in resonant circuits and filters. The equivalent series inductance, or ESL, comes from the leads and internal construction of the capacitor. At high frequencies, this inductance becomes significant and eventually causes the capacitor to look inductive rather than capacitive above its self-resonant frequency. The equivalent circuit of a real capacitor shows these parasitic elements in series with the ideal capacitance. The ESR and ESL are in series with the capacitor, and their effects become more pronounced as frequency increases. Different types of capacitors are suited for different RF applications. Ceramic capacitors, particularly those with NPO or C0G dielectrics, offer excellent stability and low losses for RF applications. They have relatively low ESR and ESL, making them suitable for decoupling and filtering up to several gigahertz. Microcapacitors provide excellent stability and high Q factors, making them ideal for oscillator and filter circuits. However, They're limited to smaller capacitance values and can be expensive. Air variable capacitors have the lowest losses and highest Q factors because air has virtually no dielectric loss. They're commonly used in antenna tuners and variable frequency oscillators, though they're bulky and mechanically complex. Electrolytic capacitors provide high capacitance values but have high ESR and limited frequency response. They're typically used for power supply decoupling rather than RF signal paths. Inductors are crucial in RF circuits for impedance matching, filtering, and energy storage. Like other components, they have parasitic effects that become significant at radio frequencies. An ideal inductor would have impedance that increases linearly with frequency according to J omega L. Real inductors have series resistance from the wire and parasitic capacitance between turns and layers. The series resistance in inductors comes from several sources. DC resistance is simply the resistance of the wire used to wind the inductor. At RF frequencies, skin effect increases this resistance because current flows only in a thin layer near the conductor surface. Core losses in magnetic materials add additional resistance at high frequencies. Parasitic capacitance exists between adjacent turns of wire, between layers in multi-layer inductors, and between the inductor and nearby conductive surfaces. This parasitic capacitance creates a self-resonant frequency, above which the inductor behaves more like a capacitor. The equivalent circuit shows the series resistance Rs in series with the ideal inductance L and the parasitic capacitance Cp in parallel with the combination. The Q factor of the inductor is determined by the ratio of reactive to resistive components. The quality factor, or Q, is a crucial parameter for RF inductors. It's defined as the ratio of energy stored to energy dissipated per cycle. Mathematically, Q equals omega L divided by Rs. Higher Q means lower losses and sharper resonance in tuned circuits. Various types of inductors are used in RF applications. Air core inductors have no magnetic core, resulting in no core losses and high Q factors. They're stable with temperature and don't saturate, but they're bulky for a given inductance value. Ferrite core inductors provide much higher inductance in a smaller package. Modern ferrite materials have low losses at RF frequencies, but they can introduce distortion in high-power applications, and their properties vary with temperature. Toroidal inductors use donut-shaped cores that provide excellent magnetic shielding. The magnetic field is contained within the core, reducing interference with nearby components. They also have lower external magnetic fields, which is important in sensitive RF circuits. Chip inductors are designed for surface mount applications where size is critical. They use various construction techniques including wound wire, thin film spirals, and multilayer ceramic construction. While compact, they typically have lower Q factors than wire-wound types. RF transformers serve multiple purposes in RF circuits: impedance transformation, signal coupling, and isolation. They present unique challenges at radio frequencies due to parasitic effects and frequency-dependent behavior. An RF transformer consists of two or more coupled inductors. The coupling between windings transfers energy from primary to secondary. The turns ratio determines the impedance transformation ratio, while the core material affects frequency response and power handling. One of the most important functions of RF transformers is impedance transformation. The impedance transformation ratio equals the square of the turns ratio. If the secondary has twice as many turns as the primary, the impedance is transformed by a factor of 4. This is crucial for matching different circuit impedances. The coupling coefficient K determines how effectively energy transfers between windings. Perfect coupling would be K equals 1, but real transformers have K less than 1 due to leakage flux. Poor coupling results in leakage inductance, which can cause problems at high frequencies. RF transformers have limited bandwidth due to several factors. At low frequencies, the magnetizing inductance becomes low, reducing the transformation efficiency. At high frequencies, leakage inductance and interwinding capacitance create resonances that limit performance. The low frequency response is limited by the magnetizing inductance of the primary winding. If this inductance is too low, the primary will draw excessive current, reducing efficiency and causing distortion. The high frequency response is limited by parasitic capacitances between windings and the leakage inductance. These create resonances that can cause the transformer response to peak or roll off rapidly above certain frequencies. Special types of RF transformers include balluns and ununs. A balloon converts between balanced and unbalanced signals. For example, connecting a balanced antenna to an unbalanced coaxial cable. An UNIN transforms impedance while maintaining the same type of signal, balanced to balanced or unbalanced to unbalanced. Transmission lines become important when circuit dimensions approach a significant fraction of the wavelength. They're used to connect RF components, provide impedance transformation, and create reactive elements. A transmission line consists of two or more conductors separated by a dielectric material. The most common type is coaxial cable, but microstrip, stripline, and twin lead are also used. Each has a characteristic impedance Z that depends on the geometry and dielectric properties. The characteristic impedance is the impedance that a transmission line presents to a signal when it's infinitely long or properly terminated. Common values are 50 ohms for most RF systems and 75 ohms for video and cable TV applications. Maintaining constant impedance throughout a system is crucial to prevent reflections. Signals propagate along transmission lines at a velocity determined by the dielectric constant of the material between conductors. The velocity factor is the ratio of propagation velocity to the speed of light in vacuum. This affects the electrical length of the line, which is what matters for RF behavior. When a transmission line is not properly terminated with its characteristic impedance, reflections occur. These create standing waves, points where voltage and current are maximum and minimum. The standing wave ratio quantifies this mismatch and indicates how much power is being reflected rather than delivered to the load. Short sections of transmission line can function as circuit elements. A quarter wave line transforms impedance according to Z squared, divided by the load impedance. A shorted quarter wave line looks like a parallel resonant circuit, while an open quarter wave line looks like a series resonant circuit. RF filters are essential for selecting desired signals and rejecting unwanted ones. They're built using combinations of resistors, capacitors, inductors, and sometimes transmission line elements. This shows a simple low-pass filter using inductors and capacitors. The inductors block high frequencies while passing low frequencies, and the capacitors provide a path to ground for high frequencies. The cutoff frequency is determined by the L and C values. Low-pass filters allow frequencies below the cutoff to pass while attenuating higher frequencies. They're used to remove harmonics and prevent interference. High-pass filters do the opposite, passing high frequencies and blocking low frequencies. They're used to block DC and low-frequency noise. Bandpass filters allow only a specific range of frequencies to pass through. They're essential in receivers to select the desired channel while rejecting adjacent channels and interference. The bandwidth and center frequency are key parameters. Bandstop filters, also called notch filters, reject a specific range of frequencies while passing all others. They're used to eliminate interference from specific sources, such as removing 60 Hz hum or cellular phone frequencies from sensitive equipment. RF filter design involves several trade-offs. Sharper cutoff requires more components, increasing complexity and cost. Higher Q components provide better selectivity, but may be more sensitive to component tolerances and temperature variations. Power handling capability may limit component choices in transmitter applications. RF amplifiers boost signal levels and are found throughout RF systems. They face unique challenges including stability, noise, linearity, and efficiency that become more critical as frequency increases. An RF amplifier takes a weak input signal and produces a stronger output signal. It requires DC power to operate and ideally amplifies the signal without adding distortion or noise. The gain, bandwidth, and power output are key specifications. RF amplifiers are classified by their operation class, which determines efficiency and linearity. Class A amplifiers conduct current for the full input cycle, providing excellent linearity but poor efficiency, typically 25 to 50%. They're used where signal quality is more important than efficiency. Class B amplifiers conduct current for only half the input cycle, improving efficiency to about 78% theoretical maximum. However, they introduce crossover distortion and are rarely used alone in RF applications. Class AB amplifiers conduct for more than half but less than the full cycle, providing a compromise between efficiency and linearity. They're common in linear amplifiers for SSB and AM applications. Class C amplifiers conduct for less than half the cycle, achieving high efficiency up to 85%, but with significant distortion. They're used in FM transmitters and frequency multipliers where the distortion can be filtered out. RF amplifiers face several unique challenges. Stability becomes difficult as frequency increases due to feedback through parasitic elements. Noise figure becomes critical in receiver front ends, where weak signals must be amplified without adding significant noise. Parasitic capacitances and inductances in transistors and circuit layouts limit bandwidth. As frequency increases, these parasitics become more significant, eventually limiting the maximum usable frequency. Proper impedance matching is crucial for maximum power transfer and preventing reflections. This becomes more challenging at RF frequencies where component parasitics affect impedance values. RF oscillators generate the reference frequencies needed in RF systems. They convert DC power into AC signals at specific frequencies and must provide stable, clean output signals. An oscillator consists of an amplifier with positive feedback. The feedback network determines the frequency of oscillation, while the amplifier provides enough gain to overcome losses in the feedback network. The Barkhausen criteria must be met for oscillation to occur. For oscillation to occur, two conditions must be met. The loop gain must equal or exceed unity, and the total phase shift around the loop must be 0 degrees, or a multiple of 360 degrees. These are known as the Barkhausen criteria. The Colpitts oscillator uses a capacitive voltage divider in the feedback network and is popular for its good frequency stability and ease of tuning. The Hartley oscillator uses an inductive voltage divider and is simpler to construct, but generally has poorer frequency stability. Crystal oscillators use the piezoelectric effect in quartz crystals to provide extremely stable frequency references. The crystal acts as a very high Q resonator, providing much better frequency stability than LC oscillators. They're essential in communication systems where precise frequency control is required. Voltage-controlled oscillators allow the frequency to be varied by changing a control voltage. They typically use varactor diodes, which act as voltage variable capacitors, to tune the oscillator frequency. VCOs are essential in phase-locked loops and frequency synthesizers. Real oscillators have phase noise, which appears as random variations in the phase of the output signal. This shows up as noise sidebands around the carrier frequency. Low phase noise is critical in many applications, especially in receivers where oscillator noise can degrade sensitivity. RF mixers are nonlinear circuits that combine two input signals to produce sum and difference frequencies. They're essential for frequency conversion in transmitters and receivers. A mixer takes an RF input signal and a local oscillator signal and produces output frequencies at the sum and difference of the input frequencies. In a receiver, this converts the RF signal to a lower intermediate frequency for easier processing. When two sinusoidal signals are multiplied together, the result contains frequency components at the sum and difference of the original frequencies. If the RF input is at frequency f_r, f, and the local oscillator is at f_LO, the mixer outputs contain components at f_r, plus f_LO, and f_r, and f_r, minus f_LO. Passive mixers use diodes as the nonlinear element and require no DC power. They typically have conversion loss, meaning the output is weaker than the input. Active mixers use transistors and can provide conversion gain, but they require DC power and may add more noise. Single-balanced mixers provide isolation between the RF and LO ports, reducing LO leakage in the output. They use a center-tapped transformer or hybrid coupler to achieve the balance. Double-balanced mixers provide isolation between all three ports and suppress even-order intermodulation products. They're more complex, but offer superior performance in demanding applications. Conversion loss or gain describes how much the desired signal is attenuated or amplified through the mixer. Port isolation indicates how well the mixer prevents signals from leaking between ports. Third-order intercept point characterizes the mixer's linearity and ability to handle strong signals without generating intermodulation products. When combining these RF components into complete systems, several important considerations ensure optimal performance. Proper impedance matching between stages is crucial for maximum power transfer and minimum reflections. This becomes more critical as frequency increases and component tolerances become more significant relative to the signal wavelength. Matching networks using combinations of inductors, capacitors, and transmission line elements can transform impedances to achieve optimal matches. L networks, pi networks, and T networks are common configurations. At RF frequencies, proper grounding becomes critical. Ground loops can couple noise and interference between circuits. Solid ground planes, multiple ground connections, and careful layout are essential for good RF performance. Different stages of an RF system can interfere with each other through radiation, conduction, or magnetic coupling. Proper shielding, filtering, and physical separation help maintain isolation between sections. Component values change with temperature, affecting circuit performance. Some applications require temperature compensation or temperature-stable components to maintain performance over the operating temperature range. We've covered the essential RF components and their unique behaviors at radio frequencies. Understanding these components and their limitations is crucial for designing effective RF systems. Remember that all components have parasitic effects that become significant at RF frequencies. Component selection and circuit design must account for these parasitics. Proper impedance matching, grounding, and shielding are essential for good RF performance. Every passive component has unwanted parasitic elements that affect high-frequency behavior. Understanding and working with these parasitics is key to successful RF design. RF amplifiers, oscillators, and mixers must be carefully designed to avoid stability problems while maintaining good noise performance and linearity. Combining components into complete RF systems requires attention to impedance matching, isolation, and interference prevention to achieve optimal performance.